So picture this. You've got your protein of interest all cloned up and tagged with a his tag, and you're ready to purify it. You lyse your E. coli cells, run everything over a nickel column, and get nothing. Sound familiar? It's really frustrating, but it's something that even really experienced scientists face. What is really likely happening in this situation is that your protein is being expressed in an insoluble form. And what I mean here is that it's forming clumps instead of staying in solution. So what now? One option is to switch the his tag for a larger solubility tag that can help your protein behave better. That's where GST, MBP, and SUMO come into play. These three tags, your GST, MBP, and SUMO, help solubilize recombinant proteins. They are complete protein domains and therefore a lot bigger than your small peptide tags like his tags and strep tags. Before we get into the details, let's talk about why solubility is important. An analogy we like to use is imagining you own the rights to a gold mine. You'd rather have the bars of gold mined instead of the gold buried deep in the underground. Makes less work for you in the end. The same goes for proteins. Soluble proteins are just like gold bars. They're just so much easier to work with and ready to use. Insoluble proteins, on the other hand, are like gold ore trapped underground. You need to dig it out and refine it, which takes more time and effort. So a lot of times when purifying proteins, we want to start out by trying to enhance solubility rather than going through the trouble of refolding insoluble proteins. Some proteins refold nicely, but others, especially enzymes, can lose their activity in the process. So tags like GST, MBP, and SUMO are really useful in promoting that solubility. Additionally, sometimes you want an orthogonal tag when performing interaction studies with other his-tagged proteins. Solubility tags, especially GST, are very useful for this purpose as well. All right, so first up we have GST tags, or Glutathione S-Transferase tags. These are one of the most popular solubility tags. GST binds to glutathione, which is used for affinity purification and downstream applications like GST pull-downs. GST is known for being really soluble and easy to express in E. coli. When added to the N-terminus of your protein, GST often helps it stay soluble. Here's how it works. GST binds to glutathione conjugated beads in a column, and then you can wash away all the junk proteins. Then adding free glutathione elutes your nice purified GST fusion proteins. But GST isn't always a perfect solution. It has a couple of quirks. One issue is dimerization. This means GST tends to stick to itself, which can cause your protein to dimerize as well, even if it normally doesn't. So if you're studying interactions or enzymatic functions that are sensitive to oligomeric states, GST might not be your best option. Another factor to keep in mind is that the glutathione used to elute GST fusions is a reducing agent. If your protein has structural disulfide bonds, glutathione could destabilize or denature it. So if you notice your protein falling apart during elution, it might be worth it to try MBP or SUMO tags instead. The next tag is MBP, or Maltose-Binding Protein. MBP is a much larger tag, but it's great at keeping protein soluble. It binds to amylose, and then you use maltose to elute it. One cool feature of MBP is its ability to coax proteins into forming crystals for X-ray crystallography, making it ideal for structural studies. Something to remember, though, is that MBP doesn't dimerize like GST, so it's a safer option if your protein's function depends on staying monomeric. But since MBP is a larger tag, it might not be the best choice for really big proteins. Finally, we have SUMO, which stands for Small Ubiquitin-like Modifier. It's the smallest of the three tags at about 12 kilodaltons, so this makes it a good fit for large, complex proteins. SUMO's small size and flexible recognition sequence allows scarless cleavage, meaning there's no extra residue left behind after you remove the tag. This is great when you need your protein without residual flanking residues left over from a protease cleavage site. In terms of purification, SUMO uses a unique recognition sequence, and it can be cleaved by SUMO proteases that specifically recognize its tertiary structure. This means that SUMO can often be cut more precisely than other tags, and that minimizes the unwanted remaining residues on your proteins. So now comes the question of what tag should you use? Your choice is really going to depend on your specific protein and what you're trying to achieve, but I can quickly summarize a few key points to keep in mind. GST tags are medium-sized and are great for a lot of applications, so it's a good go-to, but you have to watch out for dimerization, which can make it a bad candidate when studying enzymes or certain kinds of interactions. And BP tags are bigger and give your proteins a great boost in solubility. They're good for proteins that need to stay monomeric, but may not work as well for those larger proteins. And then finally, SUMO tags are small and give you that scarless cleavage. They're ideal for trickier proteins that are perturbed by residual flanking residues from the cleaved protease site. If you're doing a lot of protein purification or just getting started, check out the GoldBio website. Not only do we have a lot of high quality reagents that we work really hard to keep affordable, but we also have a lot of great resources on this topic, articles, protocols, and other guides. I'll have a link to some resources in the description for you.